Okay, everyone. So welcome back from the break, and I'm very happy to present you the next keynote speaker, Jonathan Obrist-Farner. So he's not only really good friend and colleague, but he's also Guatemalan. So he's inspiring a lot of Central American and Latino students since he started working with lake sediments and before, I suppose. The title of his talk today is going to be From Oil Wells to Lake Cores: How Paleolimnology Redefined His Scientific Career. Jonathan, as I mentioned, he's a geoscientist, sedimentologist, and also combines also data from geophysical, geochemical, geochronological methods. And he's mostly interested on climate change impacts and seismic risks in tectonically active regions like Central America. So thank you, Jonathan, for being here. And I'm going to stop sharing so that you share your slides. And
Yes.
thank you also to Marta. So I guess this first day, we can really be happy that we chose like two persons that really understand the ECRs and still remember how it was and how it is. And so thank you. The screen is yours, Jonathan.
Okay, hold on.
Yeah, I guess we can see your note.
Yeah,
The same happened to me at the beginning. Now it's great. Thank you.
yeah. Okay, so you can see my screen, yes? And can
Yes,
hear me,
correct.
well?
Mm-hmm.
Okay. So first of all, Lisette, thank you for inviting me to give this talk, and for everybody, all the organizing committee that made this possible. I think it's great that this is being organized for early career researchers. So I'm going to tell you a little bit about my scientific career and how I started with my PhD doing something completely different to what I do today, and a jump or some years that I spent also in the oil industry doing something completely different to what I do today, and how that all has helped me uh, in my research career as a scientist. So here is a beautiful photo of what we've been recently doing. So this is a UVTech platform, and we're sailing at 6 a.m. right before sunrise in Lake Isabel in eastern Guatemala, which some part of the conversation today will be about that particular lake. And it's funny, I was laughing about the photo that they said had on the introduction, because that photo was also taken in Guatemala in a small lake, in a lake that doesn't allow motorized boats. So we were actually rowing. So you saw me rowing on that photo. And we were rowing and pulling seismic equipment in the water. And it took us about 8 hours to traverse like 2 kilometers in the lake with the seismic equipment, because we were rowing. So sometimes this career certainly takes you into very wild places to do very crazy things. Hold on. Okay, so first off, I wanted to acknowledge a lot of people that have been instrumental in what I have been doing for the last several years. And from Marta's keynote presentation a couple of hours ago, one of the things that I can tell you, from her presentation, it's important, and I hope you can take away from my presentation, is that this is by no means a one-man show or one-woman show, and you need a lot of help. And there's a lot of good people out there that are willing to work with you, and I have been very fortunate that has been the case for myself. I also acknowledge a lot of the funding sources that we have had during the last couple of years. Without their support, this work would not be possible. So I will tell you a little bit about me. So I am originally from Guatemala, and about almost 20 years ago, I came to the United States to study my undergraduate degree. I actually have a Bachelor of Science in Psychological Sciences, but I also have a Bachelor of Science in Earth Sciences. So I had a dual degree, and I was lucky that during my second year as a psychological sciences student, I took a science elective class called Geology 101, and I fell in love with geology. So I ended up pursuing both degrees, but then just stayed with earth sciences as for my career. So between 2010 and 2014, I did my master's and my PhD research in northwestern China, when we were trying to reconstruct paleoclimatic changes during the Permian mass extinction. So this is very far removed from doing paleolimnological research, especially all the work that you guys showed during the 10-minute talks before the keynote. But this place was actually extraordinary. So this is just a field photo of where I was during my PhD. And you can see this is a very arid place. There's no lakes for sure in this part of the world, and it required us to camp in these deserted areas for several months every year, which was very challenging. But the geology was absolutely beautiful. What you see here is Permian strata, and for scale, this is about 200 meters thick. That's true thickness, okay? And somewhere where you see the red arrow is actually the time interval where you have the end Permian mass extinction in here. So I studied these outcrops. I measured about 7 different outcrops, working and focusing on that time interval, trying to reconstruct paleoclimatic conditions in this part of the world during that time. So this was very beautiful. And instrumental to some of the results that you'll see later, right? The skills that I learned when I was here were very, very useful for my future scientific career. So after I graduated, I joined ConocoPhillips in Houston, Texas, and I was an exploration geologist. I was working with their Africa team, and I show here some of the locations that I worked when I was there. So I did some research in Madagascar, in the Kwanza Basin in Angola, and then I worked deep water Senegal in West Africa. So I will show you a little bit of the work that I did there, and I think you'll later see why and the connections to the work that I'm doing today. So first we'll go to Madagascar. And Madagascar has a very interesting geology. It's actually one of, for me, this was the thing that made me love the oil industry. You know, there's a lot of bad things about the oil industry, but the geology that you get to explore when you work for oil companies is absolutely remarkable. So what you see here is a tectonic map giving you sort of like a framework on the left of the Madagascar region, and on the right is just the stratigraphy with some of the tectonic and volcanic events that led to the development of the western side of Madagascar. So Madagascar, during the Triassic, the Permian Triassic, was actually attached to Kenya, Somalia, and Tanzania. And it started to split apart right around the Triassic-Jurassic time. And it moved along the Davis, this is called the Davis Fracture Zone, and it moved to the south. What was interesting is that as it moved to the south, then this area here became a passive margin. But it was actually attached to Australia and India, okay? And Antarctica as well, sorry. So then as Madagascar moved to the south, then it started to split from Antarctica, Australia, and Africa, and India. And that created some times where there was a lot of volcanism. So you can actually see here the Marion Plume. And this is where Madagascar, India, and Seychelles, which is here, started to split apart. And what we did here is we looked at, so this is the area that we were looking at, and you can actually see, I'm going to go back. This is the Mahajanga Basin, And this block here in yellow is our area of study. And what we were doing is we were doing this in collaboration with ExxonMobil. So we were actually mapping and looking for potential hydrocarbon reservoirs in the subsurface. So what you can see here on the left is a structure map of the Cretaceous time. And we were actually very interested in some of these faulted anticlines and four-way complexes that existed in the deep water of the Mahajanga Basin. And these are all salt-related structures. And what I did when I was there, actually, I was trying to link some of the geology that was present in the onshore area of the basin and link it to what we were observing in the deep water area of the Mahajanga Basin. So my job was to interpret a lot of the seismic data that was from the onshore area. So you can see here the onshore area and link it to some of the geology that we were observing in the offshore area. So these red lines are the seismic lines. In blue, we had a 3D seismic volume. And here we had a little bit of information of some wells. And then I was actually mainly using some of the onshore area plus some of the red lines in the offshore area to link it. And we were trying to understand sediment pathways and sediment transport from the onshore side of the Mahajanga Basin and link it to what we were looking in the deep water. And in particular, we were interested in this time where there was uplift on the western side of on the eastern side of Madagascar, when Madagascar and India and Seychelles had a compressional event, a tectonic event, driven mainly because India was separating from Antarctica. So it was separating on one side, which created compression on the other side. And that led to the development of these very large-scale clinoforms that you can see here in the seismics, which suggests there's significant sediment input into the basin. So I'm not going to go into the details here, but this is just to show you that when I was in the oil industry, I had the great opportunity and experience of interpreting large-scale data sets and putting them all together and working with some very, very smart geophysicists that helped me to interpret and understand the observations from this geophysical data set. So then once we finished with the evaluation of the deep water in the Mahajanga Basin, I did some work in the Kwanza Basin in Angola, but then also putting some regional geological data into context. But then I was moved to work in an appraisal project in deep water Senegal. So this was actually done because in 2014, I believe, ConocoPhillips drilled a deep water well in this area, and they found a very large reservoir. So we were in charge of trying to understand the complexities of this reservoir. So I'll give you a little bit of context here. So this is Senegal. This is the country, the Gambia, and we're right at the border between Senegal and the Gambia. And you can see the SNE1 well, which was drilled in this area here, was the discovery that ConocoPhillips did. So the fan well was also another discovery, but was a little bit more complex. So it wasn't developed during the time that I was there. And when I joined the project, this is the structure map of the reservoir. So you can see here a very nice four-way closure. And in red is the gas oil contact. In blue is the oil water contact. So you can see this is a pretty large reservoir, about 680 kilometers east-west and about 20 kilometers north-south. And when I was there, I was actually the geologist in charge of drilling. I mean, not necessarily in charge, but I was put in charge of doing the drilling reports and looking at all the data that was coming in and supervising the drilling with the ships. And we drilled SNE2, SNE3, SNE4, and Bellatrix 1 when I was working with them. And this also gave me another very interesting skill, which was the interpretation of well data, logs particularly, but also their integration to seismics. So here you can see a cross section from Bellatrix 1 to SNE3, and you can see the complicated seismics, but some very interesting observations from the wells. And in this, you can see different horizons that we were able to map, correlated to the wells, but also you can see the oil-water contact, the gas-oil contact and the oil-water contact placed within the data. So it led to a lot of very interesting things, right? So you can see here some of the interpretations from the well log. So we were using gamma ray, density, and resistivity logs to interpret what we were looking in the subsurface, and then we were correlating that to some of the seismic horizons. And in the end, just wonderful, wonderful work. I mean, it is an experience that I will forever take with me. Very interesting to be in your office in Houston, looking at some of the data coming in, and talking to the ship and telling them you need to stop drilling because we've reached the target, and then you sort of like see it on your screen as they stop drilling and the data stops coming in. So it's a very, very interesting type of work for sure. So in 2016, I left my job. So I spent at ConocoPhillips about close to 2 years. And I left in 2016 because there was a lot of problems with the oil companies, unfortunately, leading to a lot of layoffs, which is something that you have to live with when you work in a place like that. But I wanted a little bit more certainty in my job, and I was lucky enough that I got an assistant professor. Now I'm an associate professor job in 2016. And that is interesting, right? I don't think I ever thought that I was going to come back to academia, but I was just trying to find a way to stay working as a geologist, and that led me to apply, and I'm very grateful for the opportunity that I was given. So when I came to Missouri S&T in 2016, I can tell you, to be honest, right? My work in northwestern China was done, and I was there with a Chinese colleague. Actually, my advisor was from China, so it was very difficult for me to go back to do similar work. And of course, during 2016, the oil companies were all shutting down research, so it was very difficult to continue or find ways to continue the research that I was doing with them. So I came to Missouri S&T with no research ideas. And I remember being in my office thinking about what are some of the possibilities, what are some of the things that I can do. And the idea to go to Guatemala started to pop into my head. And particularly this lake in Guatemala, which I actually visited a lot when I was a young kid. And I was always fascinated by its geology, its surroundings. And now that I knew a little bit more about geology, about the possibility of actually studying that lake and figuring out how it formed. So it was very nice. And it was a nice time because I was thinking about what to do. But in reality, I had no idea how to do it. And I started reading some papers about some of the work that had been done in Guatemala, and I started finding Lisette's work and some other work that became actually instrumental to everything that I did after that. In particular, that I was, as Marta had mentioned in her keynote, right? It's like reaching out to people. I reached out, and I was, I don't know, very lucky to send out an email to Mark Brenner, which I've seen in the audience in this call. And he was incredible because in reality, I emailed and I said, look, I'm Guatemalan. I want to study Lake Isabel. I have no idea how to do any lake coring. Would you be willing to help me out? And he opened the door to basically everything that I had done since then. He took my call. We chatted for a long time. and he helped me get some coring equipment to start the work. And that's how I did it, right? Nothing very fancy, and yeah, it was just more of an adventure, of a trial and error type of thing. And the reason why I was very interested in doing this is because when you look at the tectonic context of Central America, it's actually very interesting. Guatemala has one of the highest seismic risks in the world, which is quite remarkable for such a small country. It's a very dangerous place. And I don't think that people necessarily understand back in my home country how the risk of seismicity is actually how high it is in the country. And we don't do a very good job at monitoring the seismicity in the country. So some of the work that has to be done is actually very fundamental, which is very, for me as a Guatemalan, drives me every day to continue working on this, to help the people in my home country better understand seismic risk. And just as an observation for this, right, is that in 1976 there was a very large earthquake, and it killed about 23,000 people. If you actually look at the amount of people that live near this plate boundary or this fault system now, and if a similar earthquake were to occur, you're talking about like 5 to 6 million people would be affected. So this is very, very concerning. And then when you look at, so this is the tectonic context of my motivation. But then there's also climate, right? So we've seen unprecedented climate warming during the last 20, 30 years. And what this has resulted is it actually has resulted in the dry corridor of Central America to expand, which is actually leading to a lot of climate and environmental changes, and is leading also to food insecurity, and which results in a lot of emigration from Central America to particularly to the United States. So this is very very interesting, right? You have a very small country which has significant problems with climate and the projections of climate for the future, but also has the very high seismic risk. So then this has motivated my projects, right? Now I show you the Western Central American region and some of the lakes that we have been studying. And I will focus right now on Lake Isabel, which is the largest lake in the country. And as I mentioned previously, I didn't know anything about this, right? I didn't know anything about how to actually properly study a lake. So in 2017, we bought some coring equipment and we went to Guatemala. I put some drum barrels together, bought some wood, and we went and cored the lake. I can tell you many stories, horror stories about the things that we did and how we were actually able to collect cores. But I have learned now, 7, 8, 9 years later, that many of the things that we did were probably not in the best, but we still got cores out of the lake. So I will show you some preliminary, or not preliminary, but some interesting results from some of the cores that we have collected. These by all means, they're not all the cores that we have from this very large lake, but some of these cores have been very nice because they have provided some very interesting data. So I will show here, actually, Edward was also on the call, right? So this is Edward, when he was working with me as a PhD student, we were able to publish some very interesting results from one of the cores that we collected that showed very interesting hypotheses about the intertropical convergence zone and how that has shifted through the Holocene, and potentially how that has influenced precipitation in this particular part of the world. And I'm not going to get into details, but I put here the paper on the left, just in case if you wanna take a look at some of the preliminary results that we have had from this very shallow course. So some very interesting results. But we have also been able to find that the lake not only is recording hydroclimate, but it's also influenced by the Caribbean Sea. So what you can see here on this very small figure on the left is that the lake is connected to the Caribbean Sea. And in the past, the Caribbean Sea actually migrated up through the river system and flooded Lake Isabel. And that led to the establishment of this very interesting biogeochemical lake where you have a lot of changes happening. And it has led to some very interesting observations about this 8.2K event, which is a paleoclimatic event, but it's also related to a sea level jump and the establishment of anoxic conditions in the lake that preserved very beautiful dwarfs, which was actually Edward's second paper from his PhD. So some very interesting results. But all this was all brand new to me, right? There was no paleolimnological training when I started doing this, and I left a little bit of what I actually was trained to do. But in reality, there was other opportunities, right? So this is again the same lake with the same coring locations. You can see the cores here. But in the 1990s, Shell, the oil company, explored the basin for hydrocarbons. So they had a lot of seismic lines that were available to us for us to look at the deep stratigraphy of this basin. So we started working with the seismic data, and we started to incorporate some of my true training, right? What I actually was trained to do for my PhD, which is the incorporation of the seismics, the wells, and some of the outcrop information. So here I will show you some work that we did in this area here, where we were trying to correlate the seismic observations with some outcrop information. So we went in 2018 to look for outcrops that we had a colleague in Guatemala that had worked on some of these outcrops. And we were trying to find them again and try to see if we could do some work. So here is a very nice outcrop along a river in the eastern side of Lake Isabel that actually contains the earliest stratigraphy that was deposited within the sedimentary basin and later uplifted due to tectonic movement on one of the faults. But you can see that not all of it was outcrops. We actually had to walk a lot through jungle to access some of these places. And just to show you how much we've learned since then. So back, we were looking for some of the previous work that had been done. And the work that we found, it was only a few papers. And in 1918, so this was 100 years, right? 100 years difference between the first observations of some of these coal beds to when we were looking at them. And they had described these as Pliopleistocene beds based on some gastropods that were present. And this was written in 1918. But what we found is we actually found a volcanic ash that we dated, and it was actually 12 million years old. So, of course, right, the people in 1918 were incorrect, but we had significantly fancier tools to make sure that we know the ages of some of these stratigraphy. So then it started to become very interesting because now you have a basin that could potentially have Miocene strata, and it opened up a lot of opportunities. So we started to correlate some of the seismics. So here you can see the seismics again in red. And I put here in a star the outcrop location where the ash was found, or you can see here the same location in the seismic profile and in the geologic map. And we started to correlate some of the seismics. So this is a three-dimensional view of the basin, right? So you can see some of the seismic data. But we also had data from the Colorado 1 well, which was drilled by Shell in 1991. So we put all of that together and we realized that this basin had Miocene to recent sediments, which makes it very interesting, right? When you think about being able to have data all the way back, 8 million, 10 million years old, and study it all the way to the present. So we started in 2019, 2020 with the idea of actually doing an ICDP project. So you can think that in 2017, I had no idea how to do paleolimnological research. And with the incorporation of all these data sets in 2019, we wrote I think it was actually end of 2018, where we wrote the pre-proposal to ICDP. And it's crazy to think that, I was 2 years into my assistant professor position when we were starting to think about doing something like this. And it's scary. I had in many times no idea what I was doing, but I involved myself with a lot of very smart people that allowed us to write those incredible proposals. And I was led to believe that, when you write a proposal like this, you don't usually are successful on the first try. And unfortunately, we were successful. And I say unfortunately because then I was very unprepared to what was to come. But we did it anyway. So that led to the establishment of the ICDP Libre project, which looks at collecting sediment cores, right, that will likely give us Earth's a view of Earth's history from about 8 million years to today. And there are different components to this. Some of it is tectonic and seismic risk. Some of it is climate, but there's other biological components too, related to the Central American closure, and also looking at volcanic events from the Central American volcanic arc. So when you look at all of that, it's actually very interesting, very cool, right? So this is the basement of the basin. You can see here a seismic profile. And we think that if we are able to carry out this project, we're going to be able to look at all these climatic events that I highlight here, these biotic events too, and these tectonic events. And you can see here, we think that the coring some segments of the lake are going to give us about 8 million years to about 5 million years, and then we'll core some other segments that will give us about 6 million years to the present. So some of the stratigraphy here is remarkable, right? So on the western side of the basin, you can see the seismic profile from Lake Isabel, and the entire length of the core, 1 kilometer core would give you the entire quaternary, for example. So that would be a highly resolved quaternary record from the northern neotropics. So that's where we started. And in the past couple of years, we've expanded our work to additional lakes. So we have now shot seismics, for example, in Lake Atitlan, and in Laguna La Chua. So you can see here our boat and the seismic source here floating on the back. And you can see some of the seismic data that we have collected. We have gone now to collect sediment gravity cores. So we have used boats of opportunity, sometimes very large, sometimes very small. But we have retrieved a lot of cores from these lakes now. And we're starting to do this so that we have, of course, climate-related hypotheses, but we also are very focused on what are these lakes telling us about past seismicity along some of these faults in the country. And you can see here, I talked about the 1976 event, the earthquake that killed the 23,000 people. So now we have found the 1976 event deposit in some of these lakes. And we have been able to correlate it, for example, here between these 13 cores, sorry. We have been able to find that event deposit in that particular lake. So this is Lake Atitlan. And that was in 2022, 2023. In 2024, last year, we went with the large UITech platform and we collected long sediment cores from these lakes. The longest core that we collected was 27 meters. From Lake Atitlan, we collected a 12-meter core. So we are currently working on this core. So you can see here some examples. So these are the core photos on the left of the profiles with their core interpretations. I don't have a legend for this, I apologize. But these are just preliminary interpretations. This is from Lake Chichoch, and this is from Lake Atitlan. So some very beautiful, beautiful stratigraphy that we can observe with a lot of events that hopefully will give us a little bit of a perspective on past tectonic events along some of the faults in the country. And this has been, just opportunities that have presented themselves that of course I have taken, right? But I just want to remind you that a lot of this was just being adventurous and asking the right questions or asking questions and being lucky to be able to carry out some of this work. But we cannot forget as scientists that a lot of these projects require us to communicate and share with the people, right? The importance of the work that we do, especially now that science is being challenged or scientists are being challenged. I think it's important for us to remember that education and outreach is important. And through the ICDP project, we had this idea that we wanted to do a little bit more for geoscience education in Guatemala. So for the last 2.5 years, we have been developing this book. You can actually scan the QR code and download the book. It's free. It's a book that we hope to distribute in Guatemala as we continue to do work in the country so that people can learn a little bit more about the work that we do and the importance of that work for them. So with that, that's my talk. And I just wanted to highlight that my research career has certainly not been a straight path. It's been a very windy road, and I have taken every opportunity to learn. Everything has been important. It has been a skill that at some point I acquired through my scientific career that I have been able to apply to the work that I do right now. And importantly is you need to find good colleagues to work with, which is what Marta mentioned. Reach out for help when needed, which was also mentioned, right? I certainly wouldn't be where I am at without the help from others. And I was very uncomfortable when I went to Guatemala initially to core. But I think sometimes you have to be adventurous. Don't be afraid to do something out of your comfort zone. And we always have to remember that education and outreach are important components of your scientific career. And we always have to remind the general public of the important work that we do. So with that, thank you. I thank you for your attention. And if you have any questions, yeah.
Hey, Jonathan, thank you very much for your very nice, inspirational talk. And it looks like you have tons of sediments, so all ECRs send your applications to Jonathan. Not just kidding. But this is also like some tip and advice that I give you. If you see like some projects like that, where there are lots of different lakes where groups are working, then probably they're always looking for young scientists, right? So thank you very much again. Let's see if someone has like some one, two questions. I guess in the chat there is something, but maybe someone wants to talk. Let's see. If not, then
There's at
So
least there's somebody with their
yes,
hand raised.
Verena. Yes, please.
Yeah, I have a short question. So thank you for that interesting talk. I have a similar background working in petroleum geology before. So I wonder, what did you find to be the major or like biggest difference or change that you experienced when you decided to change from working in industry, so in oil industry, to really working in science?
That is a very very great question, and I think I can give you some examples. So, for example, when I was working in Madagascar, we had one or two seismic lines in the onshore area of the Mahajanga Basin. And we were trying to correlate the observations from the outcrops and from the seismics to the offshore area to try to understand sediment pathways into the offshore deep basin. And there was only a few lines that a few seismic lines that were available. And I saw we had like a portal where you could go take a look at other additional data that was available. And I realized that there were like 50 additional lines that we didn't have. And I went to my boss and I said, I think it would be very important to have those lines. So then he said, okay, let me see what I can do. The next day, I had all the lines on my desk. So they went out and they said, we're just going to purchase all of these so that you can do your work. Okay. Our purchase access, right, to the lines. So it literally took a day. Okay. And that's just an example, but the availability of data when you are in the industry is remarkable. We as scientists in academia don't have that. And the opposite to the story that I'm telling you is when I started working in Isabel in 2018, I found out that Shell had shot seismics. And it took me 3 years to come up with an agreement with Shell to donate the seismic data for us to use for this project. And you have no idea how many times I had to email the guy from Shell to be able to do this. And I think in the end, he sent me an email and said, Jonathan, the only thing that I'm going to miss is your daily emails reminding me about your if I had found more information about the seismics. So it was the difference, right? The difference of mainly the availability of data is remarkable. Yeah. I hope that answered your question, but that's one of the main differences that I see.
Yeah, I can imagine that. Thank you.
Yeah, of course.
So it seems like in the chat, everyone is impressed by your career path. So one question is how you were motivated to leave behind what you already knew, your comfort zone, right? And topics and everything, and keep on learning topics and evolve the way you did. So what was the trigger? What is your drive, like to, I don't know.
I think, when you look at, you have to remember, right? This is the same thing that I try to tell my students, and I see that actually this question is from one of my students. So when you look at a published paper, right? Sometimes we look at a published paper and it's so beautiful, right? Sometimes I read papers and I'm so jealous of the way that people write and the finished product, but you don't really see the years and years of work behind that finished product. And in a way, it's a disservice to us, because you see it and it's like, wow, how can I get there? But in reality, the way you get there is very difficult. And I think for me, it was very difficult to leave my comfort area, right? Or the area where I had trained. And it could have gone very wrong, Liz. I mean, it could have been that, I would have gone to Lake Isabel and it was sandy and we couldn't core. And then what do I do?
You don't think like that. That's why it worked, because you don't think like that.
Yeah, I understand. But I think people, you have to sometimes take those opportunities and be brave, right? And in the end, you don't really know what other opportunities will that step open. So yes, I was scared, but in reality, when I look back, and when initially when we were thinking about doing this, I thought, there's a lot that we can learn about seismicity and paleoseismicity and climate change in this part of the world that still needs to be done. So I saw the opportunity, and I think that's what drove it, right? What drove is my inspiration, or my hunger to try to answer some of those questions. And I hope that answers. Yeah.
Yes, thank you. We still have two questions. I guess the other one was a little bit answered by the other ones, but one is like, how do you decide, like very shortly, how do you decide where you drill and how deep will you go? And when you need a lot of sediment to process, how can you get it by drilling? So some money.
in this case, we were very lucky. Because the seismic data that Shell provided gave us a view of the subsurface. This basin is very shallow. So when you go with the seismic data, that the seismic equipment that academics that we have, with the budgets that we have, you cannot penetrate deep stratigraphy. So in essence, the entire ICDP project is possible because of the presence of that Shell data set. And how do you decide where to drill? Where we have some preliminary interpretations, where we're taking some very conservative, right, correlations between one line to the other. And from the information that we have from the wells, information that we have from the outcrops, and we're trying to extrapolate or take that information and project it down into the subsurface. That gives us some constraint on the age of the sediments that we're going to collect. And that sort of drives, right, where you're going to drill, like what type of sediment you want to collect. You want to stay away from the faults. And then if your target is the quaternary, for example, then we use those correlations and the knowledge from the seismics to select that coring location.
Okay, so thank you, Jonathan. Maybe you can check the chat. I guess there was like one or two that we didn't answer, and maybe you can write your answer in the chat. And so I guess we're going to continue now. Thank you again for the nice talk. And we're going to transition now to the second part of the session, pushing the boundaries, innovative techniques and sites. And with this, over to you,